Okay, welcome back. So we are immediately hit record and then take a drink is probably like cardinal sin number 73 that I commit of trying to record anything or do anything properly on the internet, but well. So far what we've looked at in the previous stuff that we've done has been force as a constant variable. Okay, so we've previously looked at force as a constant most of the time. Okay, there is an exception. And I am now wondering, can you see that I've written anything? Not maths. Anything but maths. Don't worry, I think maths is breaking, so you're all good. Number 8, dynamics. Yeah, so I've written like a sentence there. Sam, OBS is breaking. Okay, and then if I... Can we see the word hi? Yes, but very laggy. Excellent. Okay. I just want to do the stream. I just want to stream. Is that too much to ask? Apparently so. Okay, I'm gonna leave my phone showing the stream so that just in case everything else breaks. Whew. Right. Most of the time when we've been looking at forces applied to things, we've been looking at forces as a constant. So we might say, look at the moment of something. If we apply a force of 3 newtons at the end, we've looked at forces as gravity. So if something's falling under the weight of gravity, gravity is a constant force acting on a particle. But we have also looked at variable forces when considering things like springs, because when you have a spring and there was one here somewhere. When you compress or stretch a spring, the amount of force or tension within the spring is dependent on how much the thing is stretched, right? So if something's at rest, there is no force applied, but if we stretch it a little bit, a little force is applied. If we stretch it more force is applied. Except in the case of springs. Okay. In this case, force is a function of displacement, i.e. F is some function of x. Yeah, so the more it's stretched, the bigger the force, so it's proportional to some value x, so it changes with x. And we can't necessarily do the treatment of F equals ma. We then have things that are dependent, so it's going to change with respect to x. So sometimes force may also be a function of time. So say, I don't know what a good example of force with proportional to time is, but like it can be a function of both of these things. Say if I'm actually hitting something, don't know why I would be, but say you're on one of those, what are they called? It's like tennis, but you play by yourself. Swing ball. Say you're playing swing ball and I am applying a force, so every time it comes close to me, I hit it. It's not necessarily a thing of distance because the distance around won't affect it, but say every 1 second I hit the thing, that's going to be something that's proportional to distance. Or if, I can't think of another example immediately, but basically force is a function. Now what do we do? F is f of t. You could get something that is both a function of distance and time, and then that starts getting really complicated with multivariate functions, but we don't need to worry about those until undergraduate, so it's all good. So in the spring example, say you have some t equals 0, and then say this is my spring, and it's sort of stretched out to some length there, where say its natural length is this long, right? So we have this extra stretching. Then in that case, the force in this spring is going to be acting to try and shrink it, right? I've stretched it out further than it wants to rest. So the force is acting in this direction. And then I release it at some later time, t1. Then what's going to happen is my spring is going to snap back and actually shrink to less than my natural length. And in this case, once it's essentially compressed, then the force is now moving in this direction, and it's going to be going back towards rest. And what you start getting here is a spring that is oscillating. So it's moving in one direction, then the other, because it's slowly trying to return to its natural length. But if we were to model the system, we could either say, in both of these cases actually, we could say that force is a function of time. So the force itself is oscillating and changing direction over time. Or we could say it's proportional to its that length, so that distance sort of here. Okay, so as x changes value, f changes value, but also as time changes, f changes. In both of these cases, though, force can be thought of as a vector because it does have direction, so we need to be careful about that as well. So, in order to consider force, not face, as a function of either time, velocity, or displacement. I did forget there were, it can also be a function of speed as well. So we need to rewrite Newton's second law. So typically when looking at sort of problems that involve multivariate forces in one dimension, you get f is either f of t, f of v, or f of x. So in order to do that, we need to rewrite what's wrong with it. So your standard for constant values is f equals ma, right? Where a is fixed, f is fixed. But if we were going to do f of x as something, mass generally doesn't change. We're going to keep mass constant, but that means that a now has to be a function of x. So when we're dealing with equations that have functions in them, if it's a function of the left-hand side, unless it's set to a constant, which would make our lives very easy actually, but a constant can't be equal to something that changes. Something that changes has to be equal to something that changes. So we have to write f of x is m of a of x, or f of t is ma of t, or f of v is ma of v. We're saying that mass is constant, we're not rocket scientists. Yeah, exactly. There are some cool, I remember back in my day, I did Mechanics 3, the M3 paper, and that actually had a question about rockets in it. Because you modelled like your rocket as a block, and then you modelled your mass, and then you jettison the mass, and then it was like a whole thing. It was really cool. It's a fun problem, but we're not doing that today. There's enough complicated stuff happening today. I think we're good. Okay, so if we were going to write a force as a different variable, then we're also going to write acceleration as a function. So in the case that a is a function of x, well, a is a function of x. Acceleration is a function of displacement. In fact, acceleration is the second derivative. Okay, so f of x is m d2x dt squared. Or we could even write it as mv dv dx. And I think we should keep it to first order, so let's do it that way. So v dv dx. For f of t, we can write acceleration is rate of change of velocity. So f of t is dv dt. And then for v as well, we can write it in the same way, so we could do either, because both of them give you an integral in v. And I will explain what I'm doing in just a second. V dv dx, or f of v is dv dt. Okay, so where did that come from? Okay, so just as a little recap, we have if x is displacement, so that's our like distance but vectorized. V is our velocity, which is our speed vectorized, and a is our acceleration, which is acceleration vectorized. Then we have, so velocity is rate of change of displacement. So velocity is rate of change is derivative with respect to time of displacement. And we have the acceleration is rate of change of velocity. So d dt of v. Okay. Then that also gives us, this is the second order of that one. And then we get to the thing that we want to get to by doing a thing. Mechanics 3, we had experimental mechanics, theoretical mechanics, that was it. So in A level, everything was modularized. So there was core maths 1 through 4, further pure maths 1 through 3 for me. And then I had statistics 1 through 3 and mechanics 1 through 3. I think statistics, mechanics, and further pure maths all went up to like 5 or something insane. So A is d dx of half v squared, which is equivalent to v dv dx. A levels are like age 18. Yes, so 16 through 18 is A level for us. So at pre-16, I think the most you get is like very basic probability, so like rolling a die and decision trees. And then 16 through 18, you start getting taught, and then you have to do now sort of just below where we're getting to with mechanics, and then I don't know where it goes up to in statistics, actually. It's, A-level stats syllabus. Let's have a look. Measures, graphs, probability, distributions, Bayes' theorem. Yeah, so it's very probability heavy, and then also like hypothesis testing, sampling, contingency tables, and goodness of fit. Ooh, and paper 3 is stats in practice. Whatever that means. Okay. Yeah, so those are the forms that we get. So this is why when we're looking at Newton's law, when it's now a function of one of the variables, so either displacement, velocity, or time, we write it in terms of those equations. So this is essentially so that you have somewhere in the equation the x or the t, and then with v, both of them have v's, so it doesn't matter too much. It's basically whatever you're given if values for is what you would use. Okay, so just doing more aside, because if we have something that is df of x dx, as a reminder, this value is the gradient of f of your function. So say my function is something that looks like this, then my gradient will be essentially the derivative. The derivative is the gradient, so that like tangent value. So this will be the the gradient of that line at that point is the value of the derivative of that function at that point. And what that means is that if you have something that is flat here, that's going to be equal to 0. In the case where the slope is positive, then it's going to be greater than 0. And in the case where it's going down, it's going to be negative. Okay. Other notation we might use will be, so here I've done it there, so I have d dx of f of x is the same as saying f dash of x, or potentially f dot. Dots typically we use to denote derivatives with respect to time, but it can be done. And then we also have the second derivative, so this is the first derivative because we only do that function once. So d dx of d dx of f is d2 dx squared, so that you're not actually multiplying the d's and multiplying the d's and multiplying the x's. They are functions, but we write it this way. But that could also be f double prime, and that can also be f double dot. So depending what notation you're using, it can be a range of those. Call it f dash, f prime. I mix and match. I think I type out f prime, but I will say f dash because it's just a little dash, you know? What else do we need to know? Okay, yes. If we're writing in white now, f dash of x is equal to 0. It's a stationary point. And stationary points are either maximums, minimums, or let's do it a bit more what are called inflection points. And how we determine which one is which is by the second order derivative. So if f prime is the gradient of the function, then f double prime is the gradient of the gradient. So here we know it's maximum if f double prime is less than 0. It's always slightly counterintuitive. It's here if f double prime is greater than 0. So the maximum is negative and the minimum is positive, because it is. And then the inflection point is when it is equal to 0. So a bit of both positive and negative, neither, depending on who you're fighting at a given day. So those are your standard sort of key tricks about differentiating. As a recap, a general function, if f of x is x to the n, then f prime of x is nx to the n minus 1. Sorry. And then the sort of anti-differentiation, which is definitely not the correct thing, correct phrasing, sort of the opposite function is integrating. So the integral of f dx is x n plus 1 over n plus 1. So generally speaking, when dealing with polynomials, when you differentiate, you take the power down and multiply and then subtract the power. And when you integrate, you do the opposite. So you increase the power by 1 and then you divide by the power. So it's sort of a mix and match. It's very easy to forget what order to do things in. And then technically we're supposed to have a constant there as well. More complicated functions do weirder things. For the minute, I think don't worry about it. We're going to do some really strange stuff at some point. Oh yeah, the power to a 0, or if you've got minus 1 and it goes to a 0, it's log. It starts getting really weird. We'll deal with that when it comes. But okay, so that's generally dealing with integration and differentiation. When are we talking about which notation is the best and why it's Leibniz's? No. No, we're not talking about that. I refuse. You can't make me. So how do we solve them? So I told you that we need to turn our equation f of x is a of x, and that gives us some, let's do with respect to time first, it's going to be easier. That's some equation, and I want you to solve it, okay? So we might be solving for velocity, we might be solving for time. We might be solving for, at this time, what is this system doing? We might be doing, what is the particle happening? I think the example I have up ahead is find the displacement after a given amount of time. And how do we do that? Well, I told you that we can write this equation as a differential equation, m dv dt, okay? This is what's called a separable equation. And this is where, depending on how pure of a mathematician you are, your explanation of what we're about to do varies greatly. The thing that we are not doing, is treating dv dt as a fraction. However, it's about to look like I'm going to treat it like a fraction. So what I'm going to do, the way that I interpret this in my head, which I think says more about me than it should, is you take the dt and you yeet it over to the other side, and you integrate both sides. So by that I mean you then get f of t, let me do it in the right colour, you get f of t dt is equals to m dv. You can't just have dt and dv, they are the things at the end of integrals. So you have an integral with respect to time equals to an integral with respect to velocity, and then you solve. So f, depending on what function it is, will be something, some other function of time, and m is a constant with respect to velocity, so you have mv plus c. It's not a fraction, okay? It's not a fraction, but it does kind of work like one. There is a formal definition of what we're doing. This type of solution to an equation is called a separable equation. Separable? First order differential equation. And fun fact, taking advantage of the separability of differential equations was my master's thesis. I had an entire method that basically just like, what if everything was separable? Like, what if everything had this form, okay? And that is the form that things can be written as f of x, g of y, was it dy dx? And then you can always do f of x dx equals 1 over g of y dy. So basically, if you can like split out your if you can split out your two variables to left hand side, right hand side, then you can cheat and you can do this. Do I want to know what that clip is? You concern me. It's just me being bad at maths, isn't it? Yeah, oh god. Don't show my boss. This is where, like, they're going to take the PhD off me. But yeah, so for all intents and purposes, and because we're not currently doing a course on ODEs, at some point, if it's interesting, we will do this. But generally speaking, here is the form. We can use it. It's really useful. It's all groovy. Okay, let's do a worked example. So we have a particle of mass 4 kg is at rest. Just don't tell the real mathematicians. That's how I've been navigating most of this career so far. I'm sure it'll be fine. At a point O on a smooth horizontal plane. At time t equals 0, a force, and this F is 16 minus v squared newtons, is applied, and the particle moves in the direction of the force. Point like bowling ball. Yeah, basically. We things don't have volume yet. They have mass, they don't have volume. We don't care about volume. Find the displacement when v is 2 meters per second. Okay? So, particle is at rest initially, and it's yeeted with a force 16 minus v squared in a direction. And this is at t equals 0, v equals 0. and then we're told to find, so if this is at 0, then at 0, some value x where the new particle is, and we're told v is now 2. Okay, and we're told to find x. So we'll start off with using f equals ma. So we're given values of velocity, and we're also given an initial time. But the thing that we're told to find is x. So what we want is there to be a value of x in this. Now, f is a function of v. Okay, but we can write a in terms of x. Okay, so we can use that v dv dx expression. So there will be an x in this somewhere, and we have values of v. So let's sub in. So we have 16 minus v squared is equals to mv dv dx. I'm realizing this is a disgusting integral and not helpful at all, but oh well. Okay, so remember what I said. We can do separable equations if we can get all of the functions, all of the values of v on one side and all the values of x on the other. So we have to take the dx over to the other side. So we're integrating this side with respect to x.
How has it been nearly 4 years?
Because I've been streaming for 4 years next month. That's how. How wild is that? Thank you so much, Cap. Hello. Nice to see you. You've missed an absolute shit show of a start of a stream. My OBS has just completely crashed. I can't see the thing at all. It's all good. Okay, so we want x's on one side. So we have to multiply through. So we end up with 16 minus v squared dx is mv dv. Now, this we could separate into integral of 16 dx minus v squared dx, but we can't then do the integration on the other side. So this is just bad. So instead what we can do a sad face as well, is we can divide by this 16 minus v. So what we end up with is the integral dx, so nothing on that side. We could take the 1 over m over if we wanted to. We can't want to. So I can't stop the stream. I can stop the stream, I just can't see the stream. I have it up on my phone to check that I'm not doxing myself, which I nearly did earlier. Go team. My streams would never be a shit show. You have bold-faced lies. It wasn't my fault. It was Twitch. Twitch just had a breakdown. Okay, so if we divide over, then we have the integral of mv over 16 minus v squared dv. Okay, that looks like something we can manage on the right-hand side at the very least, left-hand side at the very least. So integrating nothing, it's not nothing, it's 1. So that's fine. We can leave that alone. I know what the integral of 1 is. We're all good. Integral of 1 dx. That m is just going to annoy me, so I'm just going to take that out the front. And I can't do anything else with that. So that is going to have to stay like that. Okay, so integral of 1 is x. Remember, we increase the power, so if we have nothing, we now have a value of x. And then we're going to have m times a thing plus some constant term that we need to determine. So, oh, we could sub in the value of m, actually. Let's do that. That's going to be easier. What is the value of m? 4. It's a value of 4. So, let's do it inside. Okay, so we're going to get something plus c. We need to figure out what the something is. So, let me come up here and I'm going to do some side notes. So we have the integral of 4v over 16 minus v squared dv. We're going to jump to like 17 steps ahead of calculus for the minute, but what we want is we're going to use substitution. Okay, And basically, integration by substitution is where we define a new function that is nicer to integrate. So I'm going to define u as that thing on the denominator. So 16 minus v squared. Okay, then everywhere in this that I see a v, I want a u. So I also need to find out what du is. So I'll do du dv. So I differentiate this and I get minus 2v. And then again, I treat it like a fraction and pray the maths gods don't notice. 2v dv. It's like, you know I'm going to do it. Okay, so then we sub this stuff in. So, so we have, what have we got? The integral of, we have 4v. So I'm going to split 4 into minus 2 times minus 2. Minus 2 times minus 2, v dv over 16 minus v squared. Okay, so minus 2 times minus 2 is 4. That's why I've done that. So this bit is du, and this bit is u. And the minus 2 we can just leave there. Okay, so what we end up with is the integral of minus 2 over u du. So we can integrate this. So this is even the integral of minus 2u to the minus 1 du. Okay, so remember what I said. We increase the fraction, the power by 1 and then divide by it. So minus 1 plus 1 is 0 and then divide by 0. Can't do that. That's bad. So instead, what we do is this is like a special case where when you integrate something 1 over something, it becomes the natural log of it. So this is minus 2 ln of u. And then all we need to do is substitute back in, this is the exception, correct. We substitute back in what u was. So this was 16 minus v squared. Okay, so taking that in over here, that gives us x is equal to, so the displacement is equals to minus 2 times the natural log of 16 minus v squared plus some constant c. Now, we're not done. We got told to find x at a specific value of v, but what we need to do first is get rid of that constant. So need to get rid of constant. So to do that, we need a value of x and a value of v. So we know that initially, so when x was 0, v was also equal 0. Remember, because it said at rest, at a point 0. So we define where it was at rest, so before it was hit, to be our start. So that gives us x is 0 when v equals 0. And then we want the values we have is x is something, for v is 2. So these are our 2 points in time, points in space, points in speed that we have values for. So we're going to use the first ones to solve for c. And then once we have a value of c, we'll solve for x at v is 2. So let's label these pairs 1 and 2. So sub 1, and then this is the equation that we have into star. So we get 0 is minus 2 log of 16 minus 0 squared plus c. So that gives us that 0 is minus 2 log 16 plus c, or equally c is 2 ln of 16. Yes, skip ahead like 23 chapters and you get to phase diagrams. Yeah, so we have a value of c that is correct. So then that gives us that our equation star becomes x equals minus 2 log of 16 minus v squared plus 2 ln of 16. We can probably cancel this, but I won't for the minute. And then the only thing that's left to do is sub in our second set of equations. So we're solving for x, so we leave it alone, and then we just plug in 2. So minus 2 ln of 16 minus 2 squared plus 2 ln of 16. It suddenly starts getting really disgusting to look at when you have like log modulo 1. I don't know how to make my writing less gross for that. I can like try and put a tail and then put like 1. I don't think that helps at all. Solving this quickly then, you get 2 log 16 minus 4, so 12, plus 2 log 16. Then we can do something cool, which is a log law. So, fun fact, log of x plus log of y is log of xy. And similarly, log of x minus log of y is log x over y. So I can just like rearrange those and I get log of 16 minus log of 12. Because we end up with the displacement being 2 log 16 over 12, which is 4 over 3. Which is approximately a number that we don't really care about. So, ta-da! If we needed to write it in significant figures or decimal places, then we could do that, but we won't for the minute, because it's all good. Right. That is generally how you go about solving these. It does require a good amount of differentiation and calculus, which, if doing questions like this, or getting to the point in mechanics where things start becoming functions, I highly recommend going and doing some, like, Calc 1, if you're American, or further, like, I think it's like A2 level maths. Ideally, if you were doing this for an exam, you would be taught this sort of stuff first, basically. Right, I am going to go have a break, refill my water bottle, and then we're going to do some simple harmonic motion. So we've just done first differentiation, yes, Pip, but what about second differentiation? So we're going to go do that when I get back. So I will see everyone shortly. Bye-bye. Hello. Let's get back into it. I'm stressed out staring at myself on the creepy screen. Oh dear. I'll take a screenshot to show everyone what it looks like for me in the Discord at some point. So, we've done first differentiation. But what about second differentiation? So sometimes differential equations are not as nice as just separating them and integrating them and sort of treating it like a fraction. Sometimes we have second order differentials. So second order differential equations are the rate of change of the rate of change, as I said. So they are things like d2f dx squared, or f double prime, or f double, that's the same thing again, double dot. Or sometimes we write is with respect to time. Okay, so say we have an equation, and I say we have because we will typically have, if we have equation x double dot equals constant, then integrate. So if x double dot is equals to a constant, then x dot is equals to, so integrate both sides, is equal to the integral of that constant with respect to t. which is ct plus d, and then x is equal to the integral of that again, so we just keep integrating both sides. D dt, d is an awful choice of u, so it's ct squared over 2 plus dt plus e, and we just keep adding constants in. That's all nice and easy. But what about more complicated? What about more complicated equations, like the one that we're going to see in a bit? So we might get the second order differential equation. And again, I'm like blasting through like 2-3 months of A-level content in 2 hours, so bear with me. DEs of the form ax double dot plus bx dot plus cx equals 0. This is a standard form of a linear second order differential equation where we have a second order term, we have a first order term, and we have a linear term. So this, just to write it out in full, is a d2x dt squared plus b. A, b, and c are all constants here. Dx dt plus c of x equals 0. Where a, b, c are constant and x is x of t. Okay? To solve this equation, honestly, the answer is normally memorize it. But just to go through the steps, so step 1, form the what's called the auxiliary equation. Auxiliary okay, and generally what the auxiliary equation is, what if instead of derivatives we had polynomial, is how my brain thinks of it. So every time there's a differential, we add in a lambda. So that is a, and then there's second order there, so it's lambda squared, plus b, there's a first order, there's a lambda, plus c, there's no differentials, so that's just a constant, equals 0. That is a polynomial, and we can solve polynomials. So step 2 is solve aux equation. And what we get is, so writing out properly, lambda is minus b plus or minus square root of b squared minus 4ac all over 2a. And depending on what values of lambda we get, we assume the solution of the equation up here has a different form. For some reason my scroll really doesn't want to work today. So if there is one repeated root, so there's always two values with this form of the quadratic equation. There's the plus version and the minus version. So b squared plus or minus, b minus b plus or minus. The plus or minus gives you two values. If there's only one value, so lambda 1 equals lambda 2, and let's call them, they're fine like that, then the ODE has solution of the form, so this is x is e to the lambda t at plus b, okay, where lambda 1 lambda 2 is equal to lambda, right? So that's a special case. Two real roots lambda 1 and lambda 2. Then ODD has form. So now there are two different values of lambda, so the plus and the minus version of the solution to the quadratic have two different forms. Then x is equals to a e to the lambda 1t plus b e to the lambda 2t. That's my favourite. That's the nice one. Then we yeet in complex variables just for shits and giggles. So two complex roots. So this happens, so complex numbers are when the things under the square root is negative. So when b squared minus 4ac is less than 1, we start getting complex roots. So we end up with p plus or minus qi. So they're of this form, because there'll be that plus or minus variation. The p is the b over a at 2a, and the q is that coefficient in the square root done some stuff with. Again, we're skipping a lot of calculus here. I really recommend going and looking at sort of core modules, or in a few weeks when we start doing it on stream, we'll do this in more detail. Then the ODE has the form. So here it's x is e to the pt a cos qt plus b sine qt. So basically what you'll do is a and b here, capital A, capital B, are constant. So and the lambdas are sort of determined based on the solution to the auxiliary equation. But generally when you're solving, you take your ODE, you form the auxiliary equation, you solve it, and then you say, well, x is of this form. So say you do that and you get lambda as two real roots. You say x is ae to the 3t plus b to the minus 2t, for example. Then you have two unknowns in your solution, a and b, that you need to, using case variables, determine. So for example, what I mean by that is when we have an unknown constant in our solution. So here, where you had x is our variable v plus some constant, we needed to use a known time in the system, so a known pair of solutions, to determine the unknown. So we do the same thing. But now down here, most of these solutions will have two unknowns. They have a and b. So you need two different times. And that is because it's a second order differential equation. So the number of, it's the same with the number of equations, right? The number of unknowns in a system is the number of points that I need to know more information about. It's a second order differential equation. So I need two sets of values to sort of really understand what's going on. It's a little bit, but we'll get there. Luckily, most of the stuff we're looking at, especially today, doesn't even need to worry about that. So, let's look now. Oh my god, will you please? Let's look at simple harmonic motion. So at the start of the stream, I talked about a spring. So we stretch a spring out and then we release it, and it flashes straight past its natural length, and it compresses itself. The force is enough that it compresses itself, and then because it's compressed, it wants to extend, so it extends out. And it keeps oscillating in this motion. Now eventually, when we leave it alone because it's a spring, it will stop oscillating and slowly sort of go back to rest. But that sort of motion, think like a pendulum swinging or a spring oscillating, or a trampoline, or anything that has that sort of things that get stretched out and then like bounce back, typically have simple harmonic motion. So motion is SHM if Number one, the acceleration is proportional to a distance from a fixed point, and acceleration is directed towards the fixed point. Okay, so think about that spring. The acceleration is, or the force is bigger the further away we stretch it or compress it. So the acceleration is also further away. And when we stretch a spring, force works inwards towards the natural length, and when we compress it, force works outwards towards the natural length. So force is always pointing towards the natural length. So the acceleration is always pointing towards the natural length. So that in a spring, the SHM, the acceleration is the fixed point, is the natural length of the spring. It's the rest state of the spring. Now I'm assuming that I've got a fixed end and I'm just oscillating one end, sort of like an accordion. If we let it go from rest and it oscillates inwards on both sides, it starts getting slightly more complicated, but generally speaking, the equation of motion for SHM is x double dot is minus omega squared x. Okay? Where omega squared is the constant of proportionality. So some constant that will be from the system. So if it's a spring, it might have something to do with its Young's modulus. If it's something else, a pendulum, it might have something to do with the weight or the gravity. But it's some sort of constant of proportionality. So sort of how the total system effect on the thing oscillating. So let's do some definitions. So when we're talking about motion, this is with respect to time. So this is x double dot is a function of time here. Okay? I want you to keep in mind the sort of spring, string, pendulum swinginess of it, right? It's a very periodic motion. It sort of repeats itself. We say it's oscillating. So we say that the period is the time for one oscillation. So that is t is 2 pi over omega. Not omega squared, omega. So you can think if I'm swinging something around, for example, or I'm swinging a pendulum, it's the time it takes for that pendulum to get back to where it started. So one complete loop. Very similar to sines and causes and all of that sort of, you've seen periodicity before, you've seen oscillation before. Fun fact, there's a lot similar here. Frequency then is the same as frequency in music or in sound, where it's the inverse or the number of oscillations per second. So F is 1 over T. We have the displacement x. So we could solve that equation quite simply. So we do the same thing that we had before with that auxiliary equation, where we have ax double dot plus bx dot plus c x equal to 0. And in this equation, okay, a is 1, b is 0, c is omega squared. So that's the solution that we get out. So if we do that, we end up with there are two roots. So what the solution is A sine omega t plus B cos omega t. And it's the same omega as in the equation, which is quite nice. Another way of writing it, which we generally use for single end stuff, is omega t plus alpha, where alpha and A are constants to be determined. I'm not going to go too much into that, but that is just like a little aside. Alternate form there. Okay. So the velocity v is x dot, and we also have that there is an equation v squared is omega squared a squared minus x squared, where a now is the amplitude of all the oscillations. So your amplitude, again, when you're thinking of sine waves, is your height away from rest. So that is an equation that pops up quite a lot. More usefully is your max speed. So you get v max is omega a. So constant of proportionality square rooted and amplitude. If you think about something swinging back and forth, or so say a pendulum, let's say it's swinging here. Okay, T1, T2, T3. Okay, say we're swinging a pendulum. When it's swinging, I really wish I had one, but I have my pen and we'll pretend. When it's sort of oscillating, you know that it's going to stop at the edge point. Okay, and then it swings and then it stops, and it swings and it stops. And it can sort of make sense with a pendulum where, like, okay, so it's there's the effect of gravity, so it's falling due to gravity, and it picks up speed, and then it starts having to go upwards, so it starts slowing down. So you have sort of like v equals 0 at both of these extremities, and because of that you get v max actually at the bottom of the swing. So if you think about it in terms of this equation, your velocity has this minus x squared. So the further away you are from the fixed point that you're oscillating about, the slower you are. So your fastest speed is actually when you are at rest, at your point that you're oscillating about. I'm not going to say at rest. So that is where that happens. But your greatest acceleration, so that's where you start slowing down, and then your acceleration starts working backwards. So your greatest acceleration is actually at these points. That way, where we're working inwards. Because that's where your biggest force is, pulling you back towards the thing that you're oscillating about. So yeah, Vmax happens at the center line. So let's do a problem. Already done that one. So we have a particle of mass 1 kilogram attached to one end of a light elastic spring of natural length 0.6 meters and modulus of elasticity, 150 newtons. So this is actually possibly a good point to talk of. If you remember when we were doing elasticity, we were like, springs and strings, they're both elastic, they can both stretch. What's the key difference? So the key difference, especially here, is when we say that strings don't compress, they hit their natural length, and then like you can't compress a string. When you are considering motion, when we have a spring, it's simple harmonic the entire way, right? Like it gets compressed and then it's simple harmonic still as it keeps coming outwards. When it's a string, we can stretch it. But once it starts working inwards, when it's attached to a string and it hits its natural length, it's just going to keep going. It's going to lose its force, but the string isn't going to be the thing stopping it. So if you've ever... trying to think what a good example is here. So like on a table, if you have something on a string and you've pulled it, it just kind of like goes past sort of natural compression, but maybe even keeps going past the fixed point on the other end. But it doesn't bounce back and forth. So it's just something to keep in mind that springs will be SHM their entire motion. Strings might not be. And if you can't hear the difference between what I'm saying, don't worry about it. String v spring is a mean way to do it. Okay. The other point, the other end, is attached to a fixed A on a smooth horizontal plane. P is particle P pushed towards A so that the spring has length 0.5 meters and is released from rest. A, show motion is SHM. B, find the period of motion. And then C, determine the greatest speed. Okay, so let's just write down what we have. So we have a spring with a particle P. And at rest, it's 0.6 meters, and it's just chilling. And then it's compressed to some value. So that's now 0.5 meters. So that's compressed by a length 0.1. We have that the modulus of elasticity, is that what it's called? Yeah. Of the spring is 150. We have that the mass is 1, and we have the natural length is 0.6. So all of these questions are going to start with F equals ma. Ooh. Okay, so what is the force here? So the force is acting in this direction, and it's the spring trying to extend. So it's the force within the spring trying to go back to its natural rest state. So we can use Hooke's law, which is force in the spring is lambda x over L. So we have F as a function of x, because it's going to change over time. So we have lambda x over L, and we can have mass and acceleration is the second derivative of x with respect to t. So that's our x double dot. Okay. Let's plug in some values. So we end up with 150 over 0.6, x equals x double dot. So we can also say, because it's being compressed, I can just impose a positive or a negative on my force, because I can. So we can chuck that there. So we have x double dot is minus omega squared x, where omega squared is 150 divided by 0.6, so 250. Okay, so because the equation is of the form x double dot is a constant times x, we're all good. So it's SHM. Then we need to find the period, and the equation for the period is 2 pi over omega, which is 2 pi over, now the mistake everyone makes at this point is doing divided by 250, but it's actually the square root of 250, which is some disgusting number, I am sure. So we can use a calculator. 2 pi over square root 250, which is 0.397 even. And that's seconds to the minus 1 as a term. Delightful. So that's our part B. And then finally, part C was determine the greatest speed of P. So remember what I said, that it was at x equals 0, but again we have an equation for that, so we can use V max is omega times our amplitude. Now our amplitude here is 0.1, and I know that because when we apply a force to a system, it's not going to gain any energy. So if something's swinging, or if a spring is oscillating, it's going to stay where the maximum distance. It's going to need a force to increase its amplitude, basically. So it might decrease amplitude, it might get damped, it might slow down, it might stop, but I would need to apply an additional force to the system to get it to oscillate more than it currently is. So we can say that the amplitude, at the very least, of that first pass through, the fastest it's going to get is when it hits this natural length for the first time. So that is definitely an amplitude of 0.1, is another way to think about it. So Vmax is omega A, so that's square root 250 times 0.1, which is a number, square root 250 times 0.1 is root 10 over 2. More you know. 1.58 ms to the minus 1. So even though SHM conceptually is quite a cool concept, or it's quite convoluted potentially, a lot of the problems that you see are just applying a series of equations that we've learnt. So in summary, going over a very, very brief introduction to dynamics, we started looking at force as a function. So variable force, and in particular looking at force, and I started us off with that example of a spring, and we showed how it changes over time, but it also changes over distance or displacement. We looked at the different ways of writing F equals ma, as F is a different function of different variables, in particular speed, displacement, and velocity. We had a very brief introduction to differentiation, looking again at first order, second order maximum points, and we looked at solving them separable first order differential equations. And I did some bad maths and said it was a fraction, but it's not a fraction. It's an approximation of a fraction. Then we did an example of applying a non-constant force on a particle, and solved for the displacement by using some very convoluted calculus. A few pages of that. Then we started looking at second order differentiation and how we solved that. So very brief introduction to second order homogeneous differential equations. If that right hand side was not a zero, there's a whole extra step that we didn't do, but we don't need to worry about that for now. So we just looked at a brief recap of how we would go about solving that. And then we looked at simple harmonic motion, which is motion where the acceleration is proportional to a distance from a fixed point, and the acceleration is also in the direction of that fixed point, and showed the equation of simple harmonic motion, which was the second order differential of displacement, equals 2 minus omega squared x. We introduced a few different functions, values of SHM, so in particular looking at period, frequency, velocity, and in particular maximum velocity occurring at the fixed point itself, about which the thing is oscillating, so bottom point of a pendulum or natural length of a spring, and then just looked at a particular example of a particle on a spring oscillating about its fixed point and its natural length, and solved for some values.